All right, welcome. Happy Tuesday. I know that Thursday there's an exam, and many of you are looking back at material to prepare for Thursday, but we also have to keep moving forward. So today's lecture, and last Thursday's lecture actually, are not covered on the midterm, as you know. Thank you for joining us. I imagine some of you may want to review this material after the exam on video to kind of keep it fresh, because there's going to be a little bit of a mental break on Thursday. Exam will be in class. I'll make some logistics announcements about it during the break today. So today we're going to start talking about functional dependencies and schema refinement. This will probably take 2 lectures, is my hunch. I don't remember what it took last year, but my suspicion was it was 2 lectures, or maybe a lecture and a half. This is a classical topic in database theory, actually, and quite useful in practice. And it's the answer to a lot of questions that come up very organically when you start building schemas in anything, really. So even if you start out in a world where there are no schemas like JSON, eventually over time you start asking the kinds of questions that we're going to look at today. And what I'll tell you is that the questions can feel pretty academic until you run into them yourself. But you will run into them yourself the minute you start manipulating stored sets of data. They're very, very natural questions. They're not unique to the relational model. The relational model gives us a very nice handle on how to think about them, though. So hopefully with that background, I'll be able to motivate thinking through this stuff, even though it's going to feel, I think, a little academic if you haven't built databases before and really tried to model real things with real applications and updates. All right, review. Remember we had this kind of pipeline or workflow of traditional waterfall engineering for database design. And we argued that some pieces of this also apply in more agile contexts. So we talked about requirements analysis. You go out to talk to customers, figure out what they need. The conceptual design piece is covered by the ER modeling that we talked about last time. As well as the logical design part, we talked about you could auto-translate the ER diagrams into relational. But what we left hanging last time was this idea that after having done so, there's more refinement you want to do to your schema. And we left that kind of vague, like refinement. That sounds like extra and annoying. So today we'll see why that's important. It has everything to do with data consistency and making sure that your data remains consistent in the face of updates. And the field is sometimes referred to as normalization. All right. Once you get your schema set up the way you want it, then you get into physical design, indexes, disk layouts, and possibly security design as well. All right, we're going to start today by talking about the evils of redundancy. All right, I don't know how many of you are Ruby on Rails programmers one way or another, maybe through 169 or just because you are. So there's a sort of a maxim in the Rails community called dry, right? You should make your code dry. Anybody remember what dry stands for? Don't repeat yourself. Ooh, I just repeated you. But don't repeat yourself as a software engineering maxim is if you've got the same block of code in multiple places, that means you haven't factored your software well. And you should extract that repeated code, put it in one place, so that if there are bugs in that code or if you modify that code, you modify it in one place and get it right? You're just going to get much more reliable software if you don't repeat yourself. That applies all the more so, in some sense, to data representations as well. So redundancy, in at least the relational context, as we'll talk about it today, it leads to wasted storage. If you store the same thing twice, maybe that's expensive. But storage is cheap. That's really not important. Who cares? The important thing is you get a whole bunch of anomalies that can crop up if the data is stored more than once. And you don't want to have to program defensively to prevent these anomalies. The same way you don't want to have to go fix 17 places in your source code when you find one bug. Right? You should fix it in the one place it occurs because it was only written once. So this is kind of the dry philosophy, if you will, for data. All right, and the solution to this, unlike in software, we're not going to do this by eyeball or by sort of design principles. Don't repeat yourself. Well, how will I avoid repeating myself? By not repeating yourself. Right? Here, we're actually going to have some theory that's going to help us. It's going to identify places where redundancy is inherent in our designs, right? And it's going to tell us, or at least suggest to us, how we can remove this redundancy and come up with alternative designs that are cleaner. In essence, how we can refactor our schemas. So functional dependencies are going to be the key to this. They're really a form of integrity constraint. You remember integrity constraints. They were things like keys and foreign keys and and uniqueness constraints, right? We talked about them before. So these are a particular kind of integrity constraint that helps us identify redundancy in schemas and will help suggest refinements to our schemas. Right? And the main refinement technique we'll talk about based on these functional dependencies is decomposition, which is to take a wide table and break it apart into two less wide tables that cover the columns of the original table. And this is often a good thing to do, but if you go nuts with this, you end up with tons of tables, each of which have 2 columns, or maybe 3 columns. So you can really break things down too far in some sense, and you get this very ragged-looking database with lots of little skinny tables. Some people call that the semantic web. Right? The semantic web is something where all the tables are 3 columns and all the columns are kind of the same. I don't actually think that's a good design for a database that you're actually going to be managing and manipulating. So we don't want to overdo our decomposition in most contexts. Okay, so what is a functional dependency? Well, let me give you the idea. You can read that as X determines Y. X is a set of attributes in a table. Y is a set of attributes in a table. And when you see X arrow Y or X determines Y, what it's saying is in that table R, given any 2 tuples, if they match on the X values, then they must match on the Y values. That's what that statement says. And we'll see lots of examples of this today. But the idea is if you match on the X values, then you match on the Y values in that table. More formally, a functional dependency, X arrow Y, holds over relation schema R. Notice it's over the schema. Right, so this would be true no matter what data you put in the table, no matter what instance. We're going to define this over the schema. If for every allowable instance, little r of R, so little r now is a table full of data. It's an instance of the relation. If T1 is a tuple in little r, and T2 is a tuple in little r, and when you project T1 to X, it's the same as when you project T2 to X. That means they match on the X columns. It implies that project T1 to Y equals project T2 of Y. They match on the Y columns. So this is just a careful way of saying what we had at the top of the board. Okay? Okay. Now, be careful. A functional dependency, to be clear, is on the schema. So it's being defined with respect to all allowable instances. Any state of the database must respect the functional dependencies. Anytime you do an insertion, after you're done, we have to make sure the functional dependencies hold. Anytime you do a deletion, we have to make sure the functional dependencies hold. All right, so it's over instances. You declare it. It's a rule that you write down. It is not something you mine from the data. So for example, if I give you an empty database, lots of functional dependencies would appear to hold. Right? If there are no tuples, it's true that all tuples that match on any column also match on any other column, because there are no tuples. Right? So the functional dependencies are not things you learn by inspection. They're things you write down. They're application constraints. They're there to help you keep the real world well represented in your database. Now, you might be able to go over some example data and say, gee, it looks like there are some functional dependencies here. Are they true? And then a person who understands the application domain could say yes or no. All right? But the decision about it is a design decision that you declare in a constraint. You write it down. So how is a functional dependency related to a key? Well, here's an example of a functional dependency. K, which is a set of attributes, determines all the attributes of its table R, in which case K is a superkey. All right, so functional dependencies, key constraints are functional dependencies. Functional dependencies are a generalization of key constraints. You can write a key constraint as a functional dependency. Some set of columns K determines all the columns in the table. Okay, so FDs are going to be a generalization of this idea we've had before of keys. Make sense? All right. This all starts feeling really simple, and then as you go down this road, it gets interestinger and interestinger, or curiouser and curiouser. Okay, so let's consider this relation that we had in the book of hourly employees, all right? Hourly employees have a social security number, they have a name, they have a parking lot, they have a rating, they have a wage per hour, and then they have a number of hours that they work per week. And we're going to write down, just for shorthand, we're going to write down the schema for this thing as just a string of capital letters, each capital letter corresponding to one attribute. All right? This is going to save us a lot of writing down and typing. So instead of writing SSN, name, lot, rating, wage per hour, hours per week, we're going to write down SNLRWH. Okay? Which, for the benefit of making it easier to say, I will pronounce as Snillerwood. All right? So we're going to talk about Snillerwood today a fair bit. It's our example. Just think of it as that set of attributes, all right? We can also use the relation name if we're talking about all the attributes. Rather than saying sniller, we could say hourly emps. But sometimes we'll look at subsets of the attributes, so we'll want to write them down. Okay. So what might be some reasonable functional dependencies on hourly emps? Well, social security number is the primary key. Okay, so here is a functional dependency. S determines sniller. Right? S determines all the attributes. Two tuples that match on S must match on everything. Now, since it's a relation, if they match on everything, there can't be two such tuples. There can only be one. Right? That's the whole idea of the relational. This is all pure relational model, so no duplicates. So there can't be duplicate rows. Moreover, S is a primary key. So if you match on all attributes, there's only one tuple. You can't actually match on all attributes. You are the same tuple then. But S determines sniller means that if you have S, you have all the attributes determined. All right, here's another one. Perhaps in this application, we will say rating determines wage. This is true of professors at the University of California. Actually, it's not 100% true, but it's pretty close to true. We all have steps. I'm like step 6 or something like that professor. And step 6 professor, you can look up my salary on the internet. There's a table which maps from steps to salary ranges. Okay, so here similarly, rating determines wage. All right, and all people with the same rating must have the same wage. Parking lot determines parking lot. This is true. It's also trivial. It's called a trivial dependency, but any attribute determines itself. And that follows from the relational model. You can only have one value in each cell, right? So any tuple that matches on parking lot matches on parking lot. Okay. So these are all reasonable functional dependencies on the hourly emps table. Good? We won't talk much about trivial dependencies because they're not very interesting. They do come up, though, and sometimes you can use them in proofs. Okay, now we get some problems, actually. And the problems that are going to arise in this case are due to this rating determines wage business. So here's our table of employees, sniller, okay? And you can see there's people with different ratings. Some people have the same rating, some people have different ratings, and their wages, all right? Bad things can happen. What bad things could happen because of the way we've encoded this table? It's not very dry, is it? What's repeated? Yes? Okay, well, the R's W pairs are sort of repeated, right? 8-10 is repeated. 5-7 is repeated. Agreed? So what could go wrong because we repeated ourselves? Think about changing the database. What could go wrong if we changed the database? Yeah.
If rating does determine wage, you could choose wage, which would need to be functional dependent, but not change salary, which would need to be functional dependent.
Great. So what was pointed out was if we changed Mr. Achu's wage, but we did not correspondingly change Ms. Smiley and Mr. Madian's wages, then we would have broken the functional dependency. Or if we want to preserve the functional dependency, if we give Achu a raise, we got to give everybody a raise, all right? And we have to do it explicitly. We have to go in and change all their wages, all right? So a single update requires us to make many updates, all right? So that's actually called an update anomaly, all right? You cannot modify a wage independently. That would lead to a violation of the functional dependency. What other kinds of anomalies can you imagine? What else could go wrong here? So updates are one thing we could do to this table. They could cause trouble. What other changes could we make to the table? I'll give you a hint. We can insert things and we can delete things. What would happen if we deleted stuff? What bad thing could happen? Suppose we fire some people. All right, I'm going to be more explicit. Suppose we fire, it's a bad day at the shop, and we fire both Smethurst and Gouldu. What happens? What bad thing just happened? Yeah? Okay, so the statement was the functional dependency is lost. Interesting. Did you have one you wanted to suggest? Good. Right, which I think is an expansion of what was said. So you would no longer know some of the mapping of ratings to wages that you used to know, right? We used to know that 5 corresponds to 7, right? Rating 5, people are paid 7. If we fire some people, we lose that information from the database. We suddenly lost the ratings information, the ratings wages information. So that seems bad. So that's called a deletion anomaly. Okay. Is there a corresponding insertion anomaly, do you think? Suppose I want to hire someone with rating 6. What's their wage? Haha, I get to make it up. I don't know. All right, that is not the way it works at the University of California. Okay, so if you hire a professor at a step level that no other professor's at, you don't get to make up their wage. All right, there's a rule. Everything at the U of C, it's a taxpayer-funded institution. There's rules about everything, man. And particularly there's rules about who gets paid what. Because if you don't have rules like that, you end up at the front page of the San Francisco Chronicle because they just love to bash us. I do not know why they don't do that to Stanford. Maybe because Stanford doesn't tell them what's going on. But State University, right, there's rules. So the rule is for every possible rating, there is a wage, and it is well-defined. And you do not lose it just because some professor got fired. Okay, so that's a deletion anomaly. So an insertion anomaly, that's an insertion. So deletion anomaly is that you can't lose this information. The insertion anomaly is you don't get to make it up on the fly. It has to be in the published table of rating wage pairs. Okay? So there's all 3 of these kinds of anomalies that arise because we weren't dry. We didn't have a place where ratings and wages were sort of well-defined. Okay? Okay, right. So we know why R determines W is problematic. All 3 of those anomalies. But S determines W, right? Because S determines everything. S determines all of Snurlr. So why is it not a problem that S determines W? Why doesn't that lead to, say, update anomalies? Uh-huh. That's right. We know that there's only one copy of each Social Security number. It's a primary key, right? So there can't be duplicate SW. S is, what am I trying to say? There can't be duplicate SW pairs. There's no redundancy, right? And because the S determines W is unique, S is a key, we don't care if the wage changed for a particular individual because that mapping of that individual to their wage is unique. And it is what it is. There's no other way to write it down but to write down the Social Security number and the wage. If there were no rating system, if UC was like other universities and individuals got whatever they could convince the university to pay them, right, then S would determine W, and that would be fine because there's no rules, right? The rule is every person has a wage, but every person's unique, so that's fine, right? So when there's no redundancy, this is not a problem. This functional dependency is not a problem. The problem was R is not a key, which means there are many copies of the same R, and that redundancy with respect to W then leads to these potential anomalies. Okay? So if the left-hand side of this thing is a key, it seems like it's not a problem. We don't have redundancy. We're not repeating ourselves. And we're going to use this idea now to decompose our relations in a pretty natural way. What we're going to do is that when we see this redundancy coming from functional dependencies, we'll just chop up the relation in a fairly obvious way. We're going to use functional dependencies to help us decide how to chop up the relations. We're going to chop them vertically, to be clear. RW is causing the problems, so we shall decompose Snurlr into what? What would be a good table to peel out of this? What columns might we want to set aside? R and W, right? I want that rating wage pair, that lookup table, to be pulled out of this relation. And then, if we pull that out of the relation, it's going to have R as a key, because R determines W. R also determines R as a trivial dependency, so R determines everything. Therefore, R is a key of wages. And this is the lookup table we wanted all along. It's intuitive, right? This is the UC rules for wages, or this company's rule for wages. So it's a pretty natural, obvious encoding thing to do. And if I may, again, make reference to my dear mother, she's like, when we learned all this stuff, we're like, well, yeah, of course that's how you design databases. But the nice thing is when you encode this with a theory, you can build software to go do it automatically, so you don't have to depend on my mom doing it right. right? And much as we all love awesome software engineers and data engineers, we don't want to count on their judgment because they change jobs and they go away, and some of them are not as awesome as my mom, and so on, right? Right. So it's nice to have theory and then turn the theory into software. So that's kind of what's going on. But all we did was the obvious thing: put ratings and wages in a separate table. Take wages out of hourly EMPs. Note that ratings stays here, right? For obvious reasons. We need to know people's ratings so we can look up their wages, right? You can't take RW, pull it out, and have nothing here, because then people wouldn't have wages, right? So we end up with a foreign key of ratings, which is a reference to the primary key here in the wages table. Yeah? Totally natural, obvious thing you would do. Great. You can do the same thing in the ER diagram kind of world. All right, so let's talk this through. And this is the only time I'm going to mention this in the context of ER diagrams, because as we said last time, we tend to want to reason about this stuff at the relational level, where we'll have all the tools of functional dependencies. But at least in the case of simple things, we can look at it in ER diagrams. And it's kind of interesting to look at this example, because it does something you might not expect. All right, so this first diagram you may remember from ER lecture last time. We have employees working in departments. It's our Sniller way again, but we have departments now. And employees have parking lots, so SN and L. They also have departments. And the length of time they've worked in that department has a since field. All right? We can translate, based on what we saw last time, we can translate this ER diagram into that relational schema, where we're going to smash together employees and works in because of that key constraint that says each employee can work in at most one department. And we can smash that into the workers table, where SI could be null, right? The since could be null if they work in no departments. All right, and then departments is over there. And lots are associated with workers, right? So that's all good. That's stuff we learned last time. Now, suppose we have the functional dependency that all workers in a given department park in the same parking lot. It would be really nice if there was a computer science department parking lot, I got to say, because I'm really tired of hunting for parking and fighting everyone in the university. But we don't have that. All right, but let's suppose we did. D determines L. Then what might we do to make this right? Well, the schema up there, if D determines L, look at the workers table. Key of workers is S, right? So this is just the same as R determines W. It's the same problem, right? We're going to redundantly store department computer science lot 4, right? So we want to pull that out. So we want DL to be in a separate table, and we want to take L out of employees. So we'll get something like that. Workers 2. We pull DL out into a depth lots lookup table, and then department stays the way it is. Okay? And now we want to put together an ER diagram that matches that. Well, we can fine-tune this. If department determines lot, and department obviously determines department, D is the key of both depth lots and departments, then we might as well put L in the departments table and just have one table there. At which point, our ER diagram looks like that. Lots actually migrated over to the other side. Sort of makes sense, actually, right? Lots are now determined by departments, so they kind of belong to departments in ER land. So this was a case where we wrote something down as a conceptual model, we got some schema refinement, and actually it changed our conceptual model. That's kind of interesting to keep in mind. So as you go through schema refinement, you may want to come back and show your conceptual model results back to your customer. And they'll say, oh, yeah, all right, lots go with departments. I get it. That makes sense. Okay. Yeah, well, we said that department determines lot, right? So suppose you have 2 employees in the same department. Like Professor Franklin and I are both in computer science. So by this rule, we would both park in the same parking lot. And so we'd have 2 rows in the workers table, one for Franklin, one for Hellerstein. Both of them would say CS in the department and lot 4 in the lot field. That's the redundancy. So what we want to do is pull out the association between CS and lot 4 and put it in a separate table. Okay. So that table is called depth lots. All right. So we've got the bones of this thing. We sort of get it. Let's kind of begin to crank the machinery around this little baby theory we have and see what happens. Okay. Given some functional dependencies, you can usually infer some more functional dependencies that must hold by implication. All right? So, for example, suppose we have a movies database, and we say that the title of the movie, if you know the title, then you know the studio that made the movie and you know the star of the movie. Title determines studio and star. If that's true, well, then probably the title determines just the studio. Right? It doesn't only determine the concatenation of studio and star, it determines just the studio. And also title determines just the star. That seems totally natural. All right, what about this? Title determines studio and title determines star. If we know both of those things, probably title determines the pair studio comma star too. That makes sense. So this is kind of the inverse of what we just said. What about if we know that the title determines the studio and stars are associated with studios? So if you know the studio, every studio has at most one star. So title determines studio, studio determines star, then title of the movie should determine who the star is. Also by transitivity, all right? So those all sort of make sense. Here's an example. Title comma star determines studio. So we know that, what's a good example of this? That would be a really silly example that my kids would appreciate. Maybe you would. So Parent Trap, comma Lindsay Lohan, all right, determines studio, which is, I don't know, like Warner Brothers or something. But there's an old version of the Parent Trap with Haley Mills, which is a different movie. It was made by a different studio, right? So you need the pair, Parent Trap, comma Lindsay Lohan, to know what studio it is, right? So title, comma star determines studio. Doesn't mean the title determines studio, because Parent Trap was made by two different studios at two different times with two different stars. Right? Also, star does not determine studio in this case. Maybe Lindsay Lohan works for lots of studios. Right? So these implications, you have to be a little bit careful. And so, happily, someone's already figured this all out for us. And they're called, So what we're going to want to come up with is a set of rules, which we're going to see on the next slide, that will help us reason about these implications and kind of crank out more and more functional dependencies from a set that we're given. And so what we're going to want to be able to say is that a functional dependency G, which is something determines something, is implied by a set of functional dependencies capital F. All right, when is that true? It's true if G holds whenever all of F holds. Right? And this is almost definitional. Right? We're saying the notion of implication here is whenever everything in F holds, then G holds, then we say G is implied by F. And whenever means for any state of the database, for any instance of the schema. Right? So no matter what you can put in a legal instance, this must be true. And F plus is going to be defined as following this implication rule until you get everything. So F plus is the closure of F. It's the set of all possible functional dependencies you could write down that are implied by F, including the trivial dependencies like L determines L. Right? So the closure of F is all the functional dependencies that are true based on the ones you wrote down by implication. And so we're going to need some simple rules of inference to be able to compute F plus. And here they are. They're called Armstrong's axioms, and there's only 3 of them, which is great. So this is just going to be a little simple axiom system. X, Y, and Z are sets of attributes. If X is a superset of Y, then X determines Y. This is like trivial dependencies, but more so, right? First name, comma, last name determines first name. Well, yeah, right? Joe Hellerstein's first name is Joe. I get it, right? So that's true. All right, that's called reflexivity. And axioms, of course, are things we're going to take as given. They are true. From these axioms, we will then prove stuff. Augmentation. If X determines Y, then XZ determines YZ for any Z. All right, and that makes sense, right? What's a good example? If rating determines wage, then rating, comma, last name determines wage, comma, last name. All right, not very interesting, but certainly true. And then transitivity, as we know and love, if X determines Y and Y determines Z, then X determines Z. So with these axioms, we are now armed and ready to do inference on functional dependencies. These axioms are sound and complete. Each one of them is correct. You can go ahead and prove that these hold over the sort of base definition of what a functional dependency is, which is to say, if the left-hand side axiom is true, the left-hand side functional dependency is true, then the right-hand side will hold for any instance of the relation that satisfies the left-hand side. Right? You kind of prove that sort of by brute force for those 3 things. So they are sound. They're also complete. You can't invent another rule here that will generate more true functional dependencies. This will generate all the true functional dependencies from the ones you start with. Right? And actually proving completeness here is a little bit trickier than proving soundness. And we won't prove either in class. But you can take it from me. They are sound and complete. And using Armstrong's axioms, you get only the functional dependencies in F plus then, and you get all of them. So it allows us to compute exactly the closure of F. All right? Anybody concerned about any of these, that they don't make sense? Yeah. X, Y, and Z are all sets of attributes in a table. Oh, it's just the union of them. XZ is all the things in X, union all the things in Z is XZ. Yeah, thank you for asking that clarifying question. So those are sets, and when we concatenate them, we mean union. Good. Any other questions? Okay. Well, I asserted pretty strongly that they're true, and I maybe even explained why a little bit. They are true, but you might say, gee, I can think of some more inference rules that would make sense. And you can. They're going to be macros over these, because I told you these are also complete. So there's no other rules you need, but there are other rules that could be derived from these that are pretty natural. So let's look at 2. All right? Union is a pretty natural one. If X determines Y and X determines Z, then X determines YZ. Makes sense, right? So I know that rating determines wage, and rating determines your armband color. Let's say we all have to wear armbands, and your rating determines your armband color. Then clearly rating determines wage, comma, armband color. That just makes sense, right? Can you prove union is true based on the 3 rules above? It's actually not easy. It's sort of annoying. I have to rederive it every year. So I'm going to leave that as homework. All right, prove union based on reflexivity, augmentation, and transitivity. And I'll give you a giant hint. You have to use trivial dependencies along the way. That's what they're there for, pretty much, is to prove stuff like that. So you're going to need to kind of do some X determines X kind of stuff in here to make it work. And then the proof is easy. Okay. Decomposition is more straightforward. If X determines YZ, so rating determines wage, comma, armband, then rating determines wage, and rating determines armband. All right. And this follows directly from reflexivity and transitivity, right? So X determines YZ. YZ by reflexivity determines Y. Agreed? And by transitivity, then, X determines Y. Now, this is not rocket science, nor is it really useful in some sense, but it helps you to believe that Armstrong's axioms are complete, hopefully. And you're not going to make up new rules here that aren't implied by Armstrong's axioms. Okay, so let's go through some examples now. And we'll try to learn a little bit about what we can infer from some base functional dependencies in Armstrong's axioms. So we're going to look at an example schema here for contracts, all right? And the schema is that. And just briefly, there's contracts, there's suppliers, SIDs, there's projects, so the J stands for projects, okay? There's departments, there's parts, PID, quantities and values. So C is the key. There's a contract here, and the contract has an ID, and that's the key of the relation. So C determines everything. I'm not going to try to pronounce that. I'm not going to try to pronounce that. And then here's some more functional dependencies that we're going to have. Project purchases each part using a single contract. All right, so for a project part pair, there must be exactly one contract. That's a rule that we're going to have. A project is going to purchase each part through only a single contract vehicle. All right, JP determines C. Here's another rule. A department purchases at most one part from a supplier. So if you buy, drywall from a particular supplier, you can't buy flooring from them. Okay, you can only buy one part from that supplier. So SD is going to determine P. Got it? Okay, here's the challenge. Prove that SDJ is a key for contracts. Why? I don't know. You'll see soon. But right now, let's see if SDJ is a key or not. So here we go. We know that JP determines C, we know that SD determines P, and we know that C determines everything. Do we believe that SDJ determines everything? Well, SD determines P, right? Let me use a better color this time. Which, by transitivity, doesn't determine anything, so that's not very helpful. All right, but J and P determine C. So by augmentation, is that the right word? Let's go back to Armstrong's axioms. There they are. We're going to put an attribute on both sides of an existing FD. In particular, we're going to put J over here and over here, and it's going to be true. So by augmentation, JSD determines JP. Agreed? Say yes if you agree. Yay, thank you. All right, so JSD determines JP, and by transitivity then, JSD determines C. Agreed? Yes. And what rule finishes the job here? Union, if I remember correct. Union is the thing where you get to stick stuff together at the end if they have the same thing on the left-hand side. So now JSD determines JPC. Agreed? By union. We're almost done. JSD determines JSD by trivial. All right? So JSD determines JPCSD by union again, unioning these two things. Did we get all of our stuff? Are those all the attributes? I think we might be missing something. What are we missing? Q and V. C determines everything. We could have stopped once we got to here. Thank you. You guys got to interrupt me, man. I'm just having fun. I'm just cranking the axioms out. Yes? Is it also true that DP implies S? Wow. Let's see. Is it true that that's a good question? I'm willing to entertain that question. Does DP imply S? Let's do it together. Sorry? From the description. You mean from the English?
Yeah.
Oh, so we want to ask how to interpret the English. Sorry. So like the third line here, is that what you're asking about?
Yeah.
When we say the department purchases at most one part from a supplier, what that's saying is that if you know the department and you know the supplier, there has to be exactly one part. So DS determines P. Do you agree with that?
Yes.
Okay. Now your question was, does SD determine P? Sorry. What?
DP implies S.
Does DP imply S? Is it possible? I'm going to say no because we didn't write it on the screen. Let's see if I'm wrong. DP imply S? Question mark. So is it possible to have like the shoe department orders laces from Sears and the shoe department orders laces from Walmart? Well, based on that third description, does that violate that description? I think what the description says is the shoe department buys only one thing from Sears, and it buys only one thing from Walmart. But it doesn't say how many people it could buy laces from.
So there could be two exact same parts.
Yeah. This is not, based on that English text, I don't think this is ruled out. Okay? So yeah, it's a little funny translating the English into FDs. And the thing to keep in mind is that the single thing is on the right-hand side. So it's like, if you know the things on the left-hand side, you've uniquely determined the thing on the right-hand side. Here, shoe and laces does not uniquely determine a supplier. But D and S, so shoe and Sears, uniquely determines whatever you wrote down as the part you order from them. There can only be one. Right? So if you ordered laces from Sears, you can't order anything else from Sears because we said so. Because we said these two things determine that. Good. It's good we worked through that. Thanks for asking. All right. So where we got cut off here is that this was all very nice, very entertaining, but the interesting thing here was now JSD determines the whole shooting match contracts, the whole relation by transitivity through C. Great. Sometimes it's good to see the professor do extra work because it lets us talk about complexity. All right, we'll do that in just a sec. There we go. Now, given that we have SDJ determines the whole thing, can we infer that SD determines everything but J? All right, the answer to this, if anybody ever asks you this on the street, and I know it happens all the time, like, hey man, I'll sell you an SD. Then you'll get everything but J. And you're like, wait, I don't buy it. All right, that's false. And I'll give you an example. Social security number, comma, first name, comma, last name determines salary. I'll just give you the first name and the last name. And that'll, oh, sorry, I did it wrong. Social security number, first name, last name determines social security number, comma, salary. Seems like a reasonable rule, right? I'm just going to erase SSN from both sides. All right, now what we're saying is everybody named John Doe makes the same salary. All right, which is clearly not necessarily true based on what we said before. Right? So if you drop the key from the left-hand side, for example, this certainly won't make sense, right? So you can't just drop things from both sides. This is not like division or multiplication or whatever, right? So beware. You with me? All right. Here's the thing. Talk about next is attribute closure. So, remember how I computed all that extra junk? How long do you think I would have kept going till I got bored? Pretty long time, maybe. Okay? How long? All right, that's a question of complexity. How long would the Professor Automaton need to go before he had derived all possible consequences of this thing and hopefully discovered the one he was looking for? It's a complexity question. And the answer is, sadly, exponentially long. All right? You could have had me up here for, 2 to the 7th amount of time because there were 7 attributes. That would have been really a bummer. Okay, so it's exponentially hard to compute the closure. It's not a thing we want to do lightly. It's a thing we'd rather avoid doing entirely. All right? We're going to need kind of closures, sort of, along the way to do some of our decomposition rules. Happily, computing the closure of an individual attribute is going to be useful to us. Because mostly we don't want the whole closure. We just want to know, is there some particular functional dependency in F+? Is X determines Y in F+, for some X and some Y? And for this, it's going to be good enough to determine the attribute closure of X. What are all the things that X determines? I don't want to know all of F+. I just want to know the parts of F+ with X on the left-hand side. Okay? So that's called an attribute closure. And that is not going to be so expensive. Here's how you compute an attribute closure of X, which is going to be denoted X+. All right, so X is an attribute. Remember, F is the set of functional dependencies. X is just a set of attributes. X+ is the set of attributes A, such that X determines A is in F+. All right, and here's how you compute it. Start out by setting X+ to just X, because clearly, trivially, it determines itself. And then repeat until fixed point. Repeat until no change, the following rule. If U determines V is known to be, if U determines V is in F, not in F+, but in F, in the things we wrote down. If you have some rule in F, U determines V, and U is already in X+, then add V to X+. This is just the transitivity rule. We're just going to apply the transitivity rule over and over to F, starting from X, and see what we get. And then we'll know everything that derives from X transitively. That's called the attribute closure of X. Once you have the attribute closure of X, you can just see if Y is in it. And then you know if X determines Y. Right? And this algorithm is by no means exponential. It's linear, I guess, because you can't run this loop more times than there are attributes. Right? Every time you have to add something new, there's only a linear number of things to add new, so this can't be worse than linear. This is a linear algorithm, so that's good. It's definitely not exponential. It's the combinations of stuff that causes misery. Okay. This approach can also be used to find the keys. All right? I didn't say it could be done efficiently, but it can be done to find the keys. So suppose X+ contains R, the set of all attributes in relation R. Then X is a superkey, right? So you can always answer the question, is a particular set of attributes a superkey? Next question, is it minimal? Is it actually a candidate key? How do you do that? So I give you a set of attributes like social security number, last name, first name, parking lot. And we say, hey, guess what? That's a key. How do we know if it's minimal? Yeah. Very well said. What you said was you could take turns dropping one of the attributes and see if it's still a key. All right? So in linear time, we could peel it off and make it one shorter. Agreed? Like just by dropping each one and seeing if each one is a key. All right? And if any of those is still a key, then we have to recurse and try to peel that one down further, right? Because you might get, say, 3 attributes that's still a key and say, well, is any subset of 2 of those still a key? Okay, but you don't have to look at all subsets. You can just kind of peel them off one at a time. Good. And you could do this, obviously, for any set of attributes you wanted to, starting with all of them. So you could start out with, is R a superkey of R? And the answer is certainly yes, and then work your way down from there. All right, so let's look at an example. Here's the relation R. It's got 5 attributes, A, B, C, D, and E. It's a very inspiring relation. Matches a lot of real-world scenarios. Okay. Here's our functional dependencies. B determines CD, D determines E, B determines A, E determines C, AD determines B. All right, well, this is very intuitive. Clearly, this is totally symbolic, right? Because all we're doing here now is we're just going to crank through Armstrong's axioms of transitivity and figure out attribute closures. And we don't really want to almost think about the semantics. You can get really confused thinking about, yeah, I think email does determine hair color, man, because every time I've ever seen someone with a given email, they always had only one hair color. Like, you don't want to be thinking about that right now. Just plug and chug, all right? Stay algorithmic. So as B determines E in F+, well, B determines CD, D determines E, with a little bit of work, right? So you do, now I've forgotten the third of Armstrong's axioms' names. It's the other way around. It's decomposition. It's that 5th thing there. You do decomposition and transitivity, right? So you say B determines CD, so B determines D, and D determines E, right? So B clearly determines E. So that's good. All right, how about this one? Is D a key for R? All right, let's go through this one a little more slowly. D determines what? E. All right, now we've got D plus so far equals an open-ended set starting with D and E. What does D and E determine together or singly? Really? Oh yeah, E determines C. Cool. So it determines C. Now we've got D, E, and C. What does that determine? Nothing. Well, bummer. I guess we're done, right? I guess we're done. D, E, and C. Yeah, I think we're done. So no, it's not a key. Agreed? Yeah, agreed. Good. All right. Is AD a key for R? Let's try again. AD might be more fun. We got A in here now. We already get E and C for free because we did those already. So let me throw in A. Is AD a key? What else do we get? B. Now what? C. Cool. Already got it. Anything else? We got all of them, right? We're finished. So yes, it's a key. Good. So AD is a key. Yay. All right. Is AD a candidate key? Meaning, is it minimal? All right, let's think about this for a minute. Is AD a candidate key? This is where it's good to not have any semantics. We won't try to figure this out on kind of some real-world intuition. Is AD a candidate key? How would we know if AD is a candidate key? Well, first of all, it would be a superkey, right? Did we agree that it's a superkey? We did. And now, what would make it a candidate key? D, not a key. And we know that already. We proved it. How about A, not a key? If A is not a key also, then AD is minimal, right? And we're good. And then then this thing is minimal. It's a candidate key. So is A not a key? A plus. What's in A plus? A. What else? That's it. Okay, then we win. AD is a candidate key, right? Which means it's minimal. Yay. Is ADE a candidate key? No, because AD is a candidate key, right? AD is a super key in particular. This is good enough to prove that ADE is not a candidate key. Great. All right, so that exercise closures. Yes? That's correct. The question was, suppose in some other universe that we had to prove ADE is a candidate key. What we would have to do is first prove that we'd have to prove that all pairs of two, that is to say peel off one attribute, one at a time, are not superkeys, right? So we'd have to prove AD is not a superkey, and AE is not a superkey, and DE is not a superkey. How many of those are there? There's n, right? There's 3. So if you have something that's n long, there's only n of those to check. It's not so bad. And each one of those can be checked in linear time, right? So it's n squared if you want. Good. Okay, that was nice. We just proved a whole bunch of stuff about A, B, C, D, and E. That seems like a drag, right? We learned some things about functional dependencies. Big deal, right? Weren't we talking about schema refinement a minute ago? Can this help us with schema refinement? The answer obviously is yes. It's a leading question. So we'll get back to that in the next slide, all right? But clearly this was all very mechanistic up to now. Now we'll use it. I want to take a break, though. So we'll stretch, and we'll talk about the midterm a little bit, and then we'll come back. Okay, before we talk about the midterm, I actually want to answer out loud a question I got asked. We defined this a while ago, but it's easy to forget these definitions. Just to remind you, a candidate key, maybe I should have said this up front, but it's not too late to clarify, is a superkey that is minimal. No subset of it is a superkey. That's called a candidate key. A primary key is a candidate key, is the candidate key. There can only be one. The designer calls primary. All right, so just a choice. One of the candidate keys is designated the primary key. Okay, but a candidate key is minimal. That's the whole point. It's a superkey where no subset of its attributes is a superkey. All right. Midterm. The midterm will be in class on Thursday. We are too big to fit in this room. So you will be assigned via a functional dependency of some sort, or at least a function. You'll be assigned to a room. Your, I believe, class login? The last digit of your SID will determine the location of the exam for you. Okay? And that rule will be posted on Piazza. It is already there. So you will know where to go. It's either here or 101 Morgan. All right? Those two rooms, your choice of room is going to be posted is posted on Piazza based on the last digit of your SID, your student ID. Go to the correct room. If you do not go to the correct room, terrible consequences will ensue. I'm not sure what they are yet, but be sure that they will ensue. Go to the right room so that we get the proper load balancing and don't have to recursively partition. Okay. Some of you who have DSP accommodations will be meeting in 380 Soda Hall. We will email you about that, but you heard it here as well. And that's it. Those are the 3 places you can take the test, okay? Go to the place you're supposed to go. It will be in class. It will be 80 minutes long, which is how long class is. Okay. You are allowed to bring one cheat sheet. As we said, you can put as much ink on that cheat sheet as you like. I encourage you to do it yourself and do it manually in some way. Don't just print out things, so that the cheat sheet is a form of studying. We talked about all these things. There will be TAs on hand in all three places to answer questions. We will have a shared Google Doc in these three locations. If there's any points of clarification that need to be written on the board, they will be put in the Google Doc and visible in all three rooms. During the exam, if you have questions, you raise your hand. You do not get out of your seat. TAs will come and answer your questions. If they need to be posted on the board, they will be posted on the board. It will be one person at a time going to the bathroom. What other things do we need to know logistically? We are providing you with blank backs of the sheets so that you will not be bringing in scrap paper. Just bring in your one cheat sheet. No calculators, no external brain packs of any kind. Okay? One cheat sheet and pencil or pen. Any other questions about the logistics? Yeah. You're not only do you not require a calculator, you're not allowed a calculator. There will be no books, calculators, cell phones, Apple Watches, since they haven't been released yet. None of that stuff. No Google Glass. If you need your Google Glass for medicinal reasons, please come see us.
Is it multiple choice or open-ended?
The question was, is it multiple choice or open-ended? It is not multiple choice. It may have some multiple choice questions on it. You can be sure that we will make it efficient to grade because we have to grade 350 of them, so there will not be a 3-page essay on this test. You can be quite sure of that. It will be rather quantitative and locked down, but it will not be multiple choice necessarily. The previous exam that was covered in review session is probably a good indicator of the kind of exam you'll get in terms of format. Any other questions? Okay. There's going to be a second midterm, as you know from the schedule, in April, and a final. And the policy on how it counts for your grade has also been posted since the beginning of the semester. All right. Good luck. I hope everybody gets a perfect score. I didn't design the exam to ensure that everybody gets a perfect score, but it'd be awesome if you all did, because that would mean that we're teaching you really, really well and you're working super hard. So we'll see how it goes. It's not a curve. I hope everybody does great. All right. So, functional dependencies, what the heck are they for, right? They're supposed to be for schema refinement. And so this leads us to the topic of normal forms, all right, for relations. And what a normal form is going to be is it's going to be a way to look at a relation and say, it's fine. Leave it alone. We're good now. Okay, so how do you assess if your Ruby on Rails code is dry? I don't know. You have your friend read it too, right? You kind of look around. Maybe you can get a tool that will check for repeated strings of code, but that may or may not be contextualized and make sense. We're going to have a formal notion here for a relational schema not repeating itself, not having redundancy in it. All right, and it's going to be the notion of a normal form. So we're going to define a variety of normal forms. I'm only going to make you responsible for knowing 2 of them. There are more. It gets kind of abstruse after a while. But the granddaddy normal form, which is BCNF, which we'll learn in a minute, makes tons of sense. And when you can have it, you should. And then the other normal forms make some sense. And we'll learn about only one of them, okay, because they start making less sense after a while. But if you know things are in BCNF in particular, you know that certain problems are avoided. And if it's in third normal form, at least they're somehow minimized in some way. But these things will help guide us into deciding if we should decompose things further, if things aren't okay the way they are. All right, and BCNF is really our touchstone here. It's the one we want. And it's the one sort of that comes naturally from our conversations about decomposition. So consider a relation R with 3 attributes, A, B, and C. No non-trivial functional dependencies hold. Suppose I tell you that. So clearly A determines A, and B determines B, and C determines C. But other than that, any triple ABC is good. Well, then there's no redundancy. If there's no FDs, there's no redundancy, there's no refinement to be done. You're fine. If you write down there's 3 attributes, and that's all we know about, and there's no FDs, good. No reason to decompose it. Functional dependencies, the whole reason to write them down is to constrain things. Right? And when you constrain things, you start to realize that you're writing something down that sort of is redundant. Right? Because the constraints should allow us to derive information without writing it down explicitly. All right, let me give you an example of that. What is a relation? A A relation. What is a relation? Well, it's a mathematical object, all right? But particularly a relation is, let's say a binary relation, is a pairing between values x and y, right? Everybody agree? What can I put in my relation x and y? Are there any rules on kind of what values I can put here? I mean, domain constraints, so let's say it's all integers. No, I can put anything I want. I can put 1 to 2, I can put 2 to 1, I can put 1 to 3, I can put 3 to 2, I can put anything, okay? It's a many-to-many relationship. It's all good. What's a function? I don't know. What's a function? This is where things get a little weird. A function, it's kind of like a relation, right? F of x equals y. X, y. What's a function in relational terms? Yeah.
There's only one y for each x.
Yeah. X determines y. Hence the name functional dependency. Check that out. All right? Duh. Yeah. So, what's the cosine of 360 again? Thank you. Good. So that's the cosine function, all right? Now you got to write that down for every possible x. If x is the real numbers, this gets to be a really big table, like infinitely big, right? But if you're a database geek, that's fine. What's a function? It's just a really big table, all right? If it's over a finite domain, it's a table, literally. If it's over a infinite domain, it's like a virtual table, okay? And, if you're a real database geek and you want to know what f of x is, what is that? That's input join f on x equals x, right? You can think of function invocation as a join between your input data and your function table, right? Calling functions is just really join. Everything actually is join, pretty much. All right, that's fine. Okay, I'm just saying this because it's interesting. But here's the thing, the difference between any old relation and a function is that functional dependency. You don't write that stuff down, you got a really weird piece of code, right? F of x could be lots of things. That's bad, right? If it's going to be a function, say it's a function and enforce it, right? So functional dependencies are there to make stuff make sense. It's good. When you write them down, then, you should respect them and be dry. You don't also want to have this table have that. That's idiotic, yeah? Particularly if you put a date field on here or something. So on Tuesday, the cosine of 360 was 1. On Wednesday, the cosine of 360 was still 1, right? That's a stupid database, right? Pull the cosine thing out and put the dates there and the x's, yeah? Okay, you get it. So this is not everything should have this, right? So when you write this stuff down, we want to normalize. We want to get it to the point where we have no redundancy. And if you stare at this table that we started with, it has no redundancy because x is a key, right? No. Can't have duplicates. This has no redundancy because anything goes in this one, x's and y's, anything could be here. There's no redundancy, right? Because there's no constraints. So, great. If there's no functional dependencies, we're good. No decomposition. But if you have A determines B and A is not a key, then you have this crazy business like the cosine on different days of the week, right? And so several tuples could have the same A value, and then they'll all have the same B value, and that's not dry, and it does all these sorts of bad things. Just for the record, my battery may run out anytime, but that's okay. Okay. So people started thinking about this in the 70s, and they're like, okay, well, let's write down some normal forms. Let's write down some good states of relations. First normal form, they got to be relations. All right, so if you try to write down stuff that's not relations, we're going to have a really hard time. So let's just start at the beginning. First normal form, all attributes must be atomic values, like numbers or dates or strings. They can't be nested. You can't have a tuple inside a tuple. You can't have a table inside a tuple. Right? No collection types, just atomic values in our cells. So first normal form is roughly the relational model. Okay? This is violated by many common data models you may know and love, like XML and JSON and various object-oriented models where you can have structured types inside your structured types, which is kind of cool, but it's pretty complicated to reason about things like functional dependencies. It's pretty complicated, actually, to do a lot of querying. They're just actually pretty complicated. And interestingly, some people think they're complicated even for programming. So there's a bit of a reaction, for example, in the JavaScript community or the UI programming community, where certain parties think, all these tree-shaped data structures are leading to really weird code, and it would be much better if everything was just flat, and you were not allowed to have nested arrays. So what ends up happening is they invent languages that look awfully like SQL then for building user interfaces. This is actually, I think, very natural and healthy. So it's interesting. Some people strongly disagree. So that's a software engineering debate. We don't have to get into it, but at least for data, these nested data models are going to be forbidden by first normal form, and there's at least some argument that that's a good thing. It's been a good thing for the relational database industry for nigh on 40 years, so let's assume it's a good thing for us, and we can fight about it outside of class. Okay, so all those things are not first normal form, and some of them, fair enough, are pretty useful. So sometimes non-first normal form is called NF2 or NFNF, non-first normal form. They're really useful when you want to ship stuff in a message. So suppose I wanted to put the shoe department and all its employees and all the things that it sells, and I wanted to send it from my store to your store. It'd be really annoying to send each table separately and force you to join it back together. I'm just going to roll it all up into one big JSON tree and send it to you in a single document. So that's fine. It's just a message. You're going to decode it later on. You're not going to do updates on this message, so we don't have to worry about redundancy. Right? We don't have to worry about kind of the complexity of the message because the message is just in transit. Maybe on the other end you change it around. Okay, so for moving things, oftentimes things like XML or JSON is nice. And generally in any update never, your queries are kind of canned and they all look pretty much the same. In those settings, non-first normal form can make some sense. But generally if you're going to do different kind of associations of the data, arbitrary join-ups of different attributes, nesting can bite you. Here's another thing. If you never unnest, so suppose I have a collection of JSON objects, each one of which is some crazy tree data structure, because it's got lists of lists in it. But, here's one JSON object, it's a crazy tree thing, and here's another JSON object, and it's a crazy tree thing. And I've actually got 700 of these. But all I ever do with them is send them around, and I never unnest them. Well, that's fine. That's just a relation full of squiggles, right? It's a set of squiggles. If I don't care what's in the squiggles, I don't care that they're nested. Okay, so if you never unnest anything, then the nesting's almost like it's not there. They're just opaque objects, and then you're kind of relational again. All right, so if those are your cases, then you don't have a beef. That's fine. So those could be JSON. That's all good. All right, enough said. First normal form is relational. First normal form is the basis of a whole bunch of things. So the other normal forms we'll define are subsets in some sense. They're constraints. They're more focused versions starting from first normal form. So there's a thing called second normal form, which nobody can make any sense out of anymore. So it's only of historical interest that they invented it second. So we're going to skip that entirely. And then there's a thing called third normal form, which is also kind of only of historical interest. And then there's Boyce-Codd normal form, or BCNF, which is good and makes sense and guarantees certain obvious things. So what we're going to do is we're going to learn Boyce-Codd normal form. And then we're going to say, gee, man, sometimes you don't want Boyce-Codd normal form because it's going to induce some things that are unpleasant. And we'll relax it and settle for third normal form, which is more mellow. All right, it's not as constrained, except that now we don't have very good guarantees. And I'm going to just apologize about that. Third normal form has weird promises. It makes somewhat arbitrary promises to you. Boyce-Codd normal form makes some good promises to you. Okay, so Boyce-Codd normal form. With that, let's go for the thing that makes sense. You have a relation R with functional dependencies F. We're going to say it is in Boyce-Codd normal form if for all functional dependencies in the closure of F. All right, so any functional dependency that could possibly be true based on F, the following is the case. Either it's trivial, because A is a subset of X, right? Or the left-hand side is a superkey. Either it's trivial or the left-hand side is a superkey. So here's an example of one that's good, right? We have K determines some attribute, P. But K is a superkey, so K determines everything. So that's cool, right? Because we know there's no redundancy there, right? All of our FDs in Boyce-Codd normal form have no redundancy in them. That's what this says. So it's good, right? There's none of these cases like ratings determine wages where ratings wasn't a key. Everything on the left-hand side is always either a key or it's trivial. It's P determines P, or P determines something even smaller than P, like SP determines P, which these are all trivial, right? Those are fine. But anything that's non-trivial is a key constraint and there's no redundancy. That's Boyce-Codd normal form. R is in Boyce-Codd normal form with the only non-trivial functional dependencies over R are key constraints. And if R is in BCNF, another way to think about this is that every single tuple records useful information that you cannot infer from the functional dependencies alone. Let's go back to cosine. All right? We needed a lookup table for cosine because I can't remember how it works, right? And so I have to write it down. Okay? But when we had like day of the week cosine, this was idiotic because if I just had a cosine table somewhere, I wouldn't have had to write this stuff down twice, right? There's something here that isn't a key of this table, right? So there's things we can determine. There's things we've written down that could have been determined by the functional dependencies. If I know this and I know this, then I also know that. Right? That seems a shame. That's bad. If you're in Boyce-Codd normal form, you can never do that. You can never infer stuff. Everything that's written down is something you needed to write down. Okay. So, to belabor the point, suppose you know X determines A holds for this relation. Can you guess the value of the missing attribute? If so, the relation's not in BCNF, okay? So X determines A. Can you guess the value here? What's the value here? Little a. This is not in Boyce-Codd normal form because using the FDs and some data, you can figure out other data. Got it? That's bad. That's redundancy. Okay. In BCNF, there's no redundancy. There's some connection here, and I will leave it vague because I'm not sure it's been well studied, some connection here to compression or information theory. In some sense, everything we wrote down is essential, right? There's nothing that could have been compressed out of this if it's in BCNF. I mean, other than the usual compression tricks. But there's no information here that's redundant. And with that, we will end the lecture. So I'm all out of juice. Just to finish up then, BCNF, remember, everything is either trivial or it's got a key on the left-hand side. Right? Now what we're going to want to do next, what we'll do next time, is we'll take a relation like, remember our Schneller-Ware relation, right? So we had S, N, L, R, H, W. And we said that S determines everything. And we said that R determines W. And we also said that we wanted to decompose this, right, in the natural way. We wanted to pull the RW table out and leave the SNLH table with an R still there as two separate tables, right? R is a key over here, right? R determines W. S is a key over here. There's no other functional dependencies. So this is in BCNF. All the dependencies we have are either trivial, like W determines W, or they have a key on the left-hand side. It's just that's after decomposition. Now, remember and do not forget that BCNF is defined in terms of F+. So I'm being a little fast and loose just talking about this and this. We have to actually talk about all their implications, okay? So next time we'll be a little bit careful, but I will show you a decomposition rule, which pretty much follows directly from this intuition, for decomposing relations recursively until they're in BCNF, all right? And we'll do that next time. Next time being next Tuesday. Good luck on the exam on Thursday. Office hours on Thursday, and section on Thursday and Friday will not be happening this week. For pretty obvious reasons. I don't think many of you will show up anyway. If you feel that you really need to talk to your TA or me, there will be office hours. Okay, and just come to office hours and talk to us. And as always, if you need us, you can post to Piazza an instructor question, and we'll try to get back to you. Good luck.